So what's neuron? Okay, so let's start with, this is called neural network 101, something like that. Okay, right? Now, I want you to think back to last year. Last year when you learned statistics. Yeah? You have two things. Well, you learn statistic distribution, but you learn regression as well, right? Right? That's a linear regression. Right? It's not neural machine learning by any chance. It's statistics, right? But what does it have in common? What does it have in common? Individual x, oops. I don't want this to data, each individual data point xd is Rn, right? General regression, remember that? You done this, right? Please tell me you have done it or not. Yes. Okay, you don't have to be confident in it. Have you done it? Uh-oh. Y equal to beta 0 plus beta 1 x1 plus beta 2 x2. Have you done this? If you haven't, you shouldn't register for this class. Come on. Oh boy. Okay. Okay. Right now on your laptop, Google something like general regression. This course, would be a lot less interesting by DataAnalytics. Tell you what, regardless, I'm going to make linear regression required learning, but I'm not going to waste our time doing it. So I'll make it in that time. Okay? That's the only way I think correct. If you haven't done linear regression, you should be in this class. Anyway, let's try to press on, okay? Let's see what happens. So this is what linear regression does. Okay, that's what linear regression does. You know what? it is a linear equation, right? All right. I'm thinking that we may have to tone down the project-based thing a little bit, because I don't think you guys are ready to do a project. Okay, you guys follow me here on the screen, right? let's say this were your, let's say this is what you are faced with. Okay, can you see that? Right? And you are a baby, right? I gave you 7. You tell me -5. I said wrong because this one is the answer, right? I gave you another point, which is this. It's 5 point something, but I don't tell you this. I tell you just this thing. Right? I tell you 5 point something, and you give me something like 15. I'll say, nope, it's wrong, because it should be 12. Right? If I tell you, I show you this example, and I say x is equal to 1.5, and you give me 10. I say, oh, it's wrong, but it's close. I give you -3, and you say 1. Oh, perfect. Right on. Very good. Good job. Okay. So you can see that there's a relationship between x and y that you should build in your head. If I give you this ahead of time, just a whole bunch of them, right? And I just say yes, no, yes, no, no, yes, no, yes. After a while, if you're smart, and babies are smart, it will start to notice the pattern that the bigger the x, the bigger the y. Right? The bigger the x, the bigger the y. If it's really smart, it would also notice that even if you don't give me any x, in other words, if x is equal to 0, y is still positive somehow. So y is a positive function of x, and it also has a positive intercept, right? And if the child is really smart, maybe it can estimate that, you know, it's a 1-to-1. So this thing grows by 10 points, that thing also grows by 10 points. Just by experience alone, right? This is what you would have to do as a child or a learning machine, whether a neural network or not. This is your job. This is your job. Your job is to do this. Okay? Learn this representation. X is a function, y is a function of x. And then, if I give you a new x, you have to give me the new y. That's correct. That's your job, right? Unfortunately, if you memorize the whole thing, there's going to be a problem, because this is random. So sometime when x is equal to 4, you get this. Sometimes you get that, right? So if I ask a child to memorize, is that good? Is that learning? No, that's a memorization. So remember, what's essential about learning? It has to be internalizable and generalizable, right? It's internalized in the sense that you have to know the function. Generalized in the sense that you have to be able to use it in a general context. Now, because this has a noise, what do you think the child best do? Learn the entire memorization, or learn that there's a linear pattern? Yeah, linear pattern, right? Now, linear pattern will get none of this perfectly correct, but it's good, because if I give a new point, say 4, it should be around here. It shouldn't be down here. It shouldn't be any one point. So, learning is internalization and generalization. Whatever previous lecture. Okay. So, I'm asking the machine to learn a line. Okay? I'm asking the machine to learn a line. Right? Is this line as good as it gets? Common sense would say no, right? And in fact, it's not. It's not good. Okay? With experience, a child would be able to adjust the curve, the slope to be steepened a little bit, right? So it's like an iterative process. Fortunately, for this class, for this example, okay? If a lot of time you see this in real life, okay? You see this in real life. And if this is like a height of your parent, this is your height. So you have, except it doesn't go to 0. You have this correlation between your height and your parent's height, right? But it's not perfect. Okay? For homework tonight, write me something about Sir Francis Galton. Yeah? If you like it or whatever, that's your homework. Be fine. That's his, I don't know, I don't remember his picture. I wasn't born there. Yeah, Francis Galton. But yeah, presumably that's him. I don't know what he looks like. Okay, so tell me something about Sir Francis Galton. That's your homework. Yeah, anything useful. I don't know. I don't care about his parenting. His parenting. What's his scientific contribution? Yeah, what's that? Yeah. Moreover, what's it got to do with what I just said? Right? Not now, not now. You have plenty of time. It's easy assignment. Don't worry. Don't worry. Anyway, so what I want to do is fit this thing. Right? Fit 1, fit 2, and data. So this is like, can you guys see this? I hand drew the equation, right? Y estimate, this is the Y hat with the Vietnamese or Chinese hat, right? Is equal to beta. Well, let's just ignore this. Beta 0 plus beta 1 times X, right? It's not going to fit perfect because it's just a line, right? It's going to miss. Now, so that's the error. Now, in this case, I'm just plotting an angular gauge to say what's the minimum error. That's the red arrow. Because I know I created this data. I know what the perfect line is. And the minimum error is this. You can't get it to 0, but you can certainly get it close. So now it's not so close. So this is an, well, forget this one. So you can see, yeah, this is what I said earlier. For every point that you give me an estimate is the line, y hat. What's the real y? It's the point. What's the distance? It's that line, that vertical line, right? So I square this, I square this, I square this, I square this, square, all of that, and I add them, and that gives you this value here. This value. Whatever unit, don't worry about it. Okay? Now, what happened if I move this thing up a little bit? The error is going to be less, right? So let's see if we can play with that. Okay? Oops, close. Huh? That's good. Huh? Oh, that's bad. That's not good. That's terrible. Actually, that one's perfect. You know how I know it's perfect? Because this is the parameter I use to generate. So I cheat a little bit, right? Because I create the problem, I know the final answer. So right now, the error is as good as it gets. Right? See? So this is the best line I can do. So in a way, actually, I'm having a second thought. Maybe not knowing linear regression is a good thing. Because you're learning from scratch what it means to do linear regression. Now, because this problem happens a lot in nature, happens very common problem. Instead of sort of like twiddling the slope one at a time, yeah. If I twiddle the slope, imagine originally I started flat and I get closer, the error is less, right? Pay attention to this. When the error gets less, what's another word, synonym for less? Lower? Come on, English. Close, another one. When you go downhill, descend. Yeah? Remember that word because that's going to become the key word. Right? The algorithm tries to descend the error function to make it lower. So, in fact, it's going lower down this hill. Right? And it's stopping where it is perfect. Perfect meaning that this error term, this as low as it gets. Yeah, don't blink here. Lastly, when we maximize and minimize something, what happens? The slope is 0. Right? Could be a top hill, but let's assume that it's a valley, so you can't get it. It's a valley, right? So, what is the minimum error? It's the point that the error function with respect to the change in the parameter as the 0 slope. What parameter did Sir Francis Galton give us? Beta 0 and beta 1. He gave a long one. Okay? So, the linear regression starts with beta 0 and beta 1 being unspecified. Let's set them all to 0. Then change it a little bit at a time until you get to the point where you can't change it without making the error worse. It's like saying that error is already the best. It's at the bottom. If you move this way, you go up. No good. If you move this way, it goes up. No good. Right? So you can imagine that this is a beta. One axis is beta 0. Right? One axis is beta 0. You go this way, it gets higher. Go this way, it gets higher. The other axis is beta 1. I don't know which one is which. Okay? You go this way, it goes up. Go this way, it goes. So there's a minimum point somewhere. So this is where calculus is. Right? So you start with some kind of unspecified beta 0, beta 1. You descend down the error function until you get to the point where at the bottom. How do you know you're at the bottom? Because there's no further direction of descent. You're at the basement because there's no more stairs going downstairs. You can't go downstairs further. That's the definition of bottom. Okay? Wherever you go up. Right? That's what machine learning in a supervised learning context. Right? Supervised because we mentioned it earlier. For the regression problem, because the output is y, it's a continuous number. So this is how it's done. This is how machine learning is done. Having said that, this structure of the problem is so simple and so ubiquitous, meaning it's everywhere, that instead of starting at 0 and make a little step to the bottom, you use calculus and say, where is the bottom? So you take partial difference. Yeah. อันนี้ไปไหนนะNew share. No, I have to do this one. So, yeah. Okay. Clear. Yeah. partial error with respect to beta 0. Partial. This is like a difference when you do it when you have more than one, equal to 0. Right? And if you do that and you solve simultaneous equation, you get beta 0 perfect, beta 1 perfect. So do you have to go a little step at a time? You don't, right? Because calculus is powerful, right? Calculus is so powerful that you don't have to go a little step at a time. You can go one step at a time, right? Is this the best solution there is? It is guaranteed to be the best solution there is. And the reason is because the error function looks like this. So all you have to do is find where the slope is equal to 0 in both dimensions, both axes. And you're done. So, why can't mathematician calculates all this for all the problems in life? And you don't have to do this machine learning. It's like why can't you know the perfect solution, right? Why do you have to teach a child a little bit at a time? Why can't you just boom, he's born hitting a Ph.D.? How can you do that? Because in real life, problems can be more complicated. If you follow this strategy and your error functions look like this, you're dead, right? Because you don't know where to go. Okay? Now this you can see where to go because it's small, it's one-dimensional. But remember, this is multi-dimensional. How am I going to know to go here, not here, not here, not here, not here, not here, not here? Right? Sometimes it gets worse. It's like this. Yeah. This looks good. But if you move a little bit, you get much better. Yeah. So you have the conundrum, which is if the problem is complex, you can use right away one step. Okay? Now let's go back to Sir Francis Galton, which is 200 years, whatever. Because that problem is so ubiquitous, and calculus is already invented, we have the formulas of beta 0 and beta 1. And that beta 0, beta 1 is done by, it's called ordinary least square. Least square because the error is sum of square error. So this S, sum of square error, and ordinary least square is the same word. Okay? And forget about ordinary for now. Least square just means minimum, right? So you're minimizing the sum of square error. And that gives you the perfect formula. So you have this thing, when you look up, okay, there should be a little bit footnote that say, this is assuming you want to do this, and you're minimizing sum of square error, then you use this formula. Okay? And if you did this, again, I want you to not just follow the techniques and things I'm teaching. I want you to think a little bit. This is the fundamental difference between statistical modeling and machine learning, right? Statistical modeling is powerful. It's more powerful than machine learning in this sense, because in one step you get to the right answer. It's the most powerful, get you right in the minimum error. But it's the least powerful in the sense that you can only apply to one situation. But the world is, the mathematicians are not stupid. They calculate it for this because even though it's the simplest, it's also very complicated. Right? But on your height, your parents' height, chances are I'm going to get a straight line. I'm not going to get something funny. Right? So it is a trade-off between how common it is, how simple it is, how well established, and how much you want to restrict. And this is a judgment that separates the men from the boys. You can learn all the techniques you want. In real life, like, I'm now a consultant, right? Nobody's telling you what to do. That's the real skill here, guys. Right? That's the real skill. I want you to learn how to develop this skill. You won't have this skill. But if you don't know how to develop this skill, even if you pass through another 5 years of problem, you still won't be a good consultant, or you won't be able to crack the problem. Okay? My job depends on me being able to crack the problem. By which I mean, for this problem, okay? So if I come across a problem that is really, am I gonna like bring out my fancy neural network just to impress the client? People do that, by the way. Stupid data scientists and consultants try to sort of like look fancy, and it's stupid. Okay. So this is the difference between machine learning and statistical modeling. Okay. Anybody has complete irrepressible bowel needs, movement, the toilet badly, you're gonna wee in your pants? No? Okay. All right. We'll keep going because we kind of like wasted a lot of time. So let's go back to this. Oops. So you got this one, yeah? You saw this, right? Now, imagine that this is a common situation. Okay? And so is this. Let's say this is another common situation. If this is a common situation, mathematician would have given you the perfect solution as well. Okay? But this is not a common situation. And neither is this, right? Okay? So, for the machine learning, remember, you're dealing with tabular data, linear, it's very nice, but now you're dealing with difficult problems. This is where the machine learning comes. That's the whole point, right? I'm teaching you difficult things because it covers more situations. But under the same situation that you can use linear assumption, the linear regression trick, you can't beat linear regression. Anyway, this thing is called linear regression, right? So linear regression in a statistical modeling sense is using beta 0 and beta 1 that's given to you hundreds of years ago. That's machine learning. But the problem is the same in machine learning. Okay? Problem is the same in machine learning. Okay? The problem is the same because we have X that's numerical. We want to get Y that's numerical. Now let's go to another situation where we also have statistical model. But instead of doing regression, let's do classification. Right? Let's do classification. Now in this, I don't think I have got immediate example later. In classification, I want to draw a partition. Right? I want to draw a partition. I want to separate this part into two groups. First of all, in classification, I can classify you into different animals, right? So it's M class, right? M class, let's say M class classification. But the most basic is two class, which is binary. And a lot of times, we start with binary. Okay? So binary is I'm going to separate you from you So there's only two classes, right? In traditional marketing analysis, we have some insight. I've taught students for God knows. Actually, I started teaching before I graduated. I taught students when I was a student. So I kind of know. I say, you know, based on my experience, I can tell without grading that this guy did an A, this is a fraud. This guy did B, and this guy did C. From my experience, just from my experience. Who told me this? I learned from experience, right? I learned from experience. So I prejudge you. Is that fair? No, it's not fair. You may be a terrible student, but you happen to sit here because nobody wants to sit with you. You have to sit up front. Okay? You can be over there because, I don't know, probably well. So I don't want to have prejudged model. I want to learn from the data. If I were to learn from the data, it would be something like, where you sit, I give you an exam, get various grades. Now, because it's a binary, right? If it's ordinal, I can do A, B, C, D, E. But let's say pass or fail. Okay. And let's say for some reason where you sit determines your grade. So that once I've learned this is my learning. This is my learning path. I learn how to separate pass from fail. Next class come in, next students come in. Right, next students come in, next class, next year come in. I would make the projection or prediction based on where you sit. Based on where you sit. Okay? The assumption is very minimal. The only assumption, the only one and only assumption in machine learning is called representation. Meaning, what you learn from is representative of where you need to go. So if I learn this, and I invite a new class of people, and you guys are different people, right? And not only you have different kind of thinking, okay, different schools, it wouldn't work, right? In fact, chances are, applying for next year won't work either. But let's say it's stationary, that's it. So based on this distinction, I'm going to make a cut between the pass and the fail. Once I've learned it, I will use it for next class. Okay. So it is a classification problem because the output is not a number, it is a pass or fail. How do I separate the students? Now, why did I mention the, let's make this A, B, C. This is easy, right? Easy to do that. Just say first row, second row, third row. So what's easier than that? It's nothing. It's a straight line. What's a little bit more complicated than a straight line that goes vertically or horizontally? It's the one that goes diagonally, right? Yeah, that's a bit more complicated. It's still a straight line. So if I were to do this, and let's say you over there, let's say you in the black, okay, between black and brown, guys, okay, from the brown guy to you here on the left, let's say you fail or you pass, what you prefer? Okay, you prefer to fail, fine. Now that's from you. Okay, this side, the right-hand side of this line is a passer. Failure and a passer. Failure and a passer. Right? All I need to know is draw that line. But unlike regression, I'm not trying to minimize the distance or point to the line, right? I'm not, right? I'm not, right? What am I trying to do? I'm trying to do this. I'm trying to create a line such that the one to one side of the line gets a 1. The ones to the left side or the other side of the line gets a 0. It's called a partition function. Okay? I'm trying to create a partition graph. I'm trying to create a partition graph. Now, if life were easy, this would be a perfect path, right? Everybody over here passed, everybody over here failed. A less than perfect would be maybe one or two strips. Maybe you over here, maybe you over here, maybe error. Right? But it's still the best I can do because there's no other straight line that will get the minimum error. So this is the best I can do, right? What I like to do is basically minimize not the distance of the line, but the difference between the actual score, 1 or 0, and the model score. So if I'm over here, everybody here gets to make it 1. You will get 0, right? But in real life, one of you gets 0, even though you're on the right side. One of you gets a 1, even though you're on the left side. So that's my error. I can't do any more than that. Yeah? In fact, I don't want to do more than that because that's not generalizable, right? It's overloaded. So what can I do? What can I do? What can I do? Well, let's draw some line. Yeah, let's draw some line. Yeah, let's say this is x1, x2, and this is 3, and this is 4. Okay, what's the equation of that line? Come on. Guys, this is not last year, this is high school. Okay, I'm, so it's what? Y, okay, we call this y, just to make it simple and call this x. Okay, but y is not a function of x now, you understand? Y is different. Okay. So what's this line? Y is certainly equal to 3, right? Right? What? Minus, come on, 3, 4, right? X, am I right? Okay. So let's move things around a little bit. Let's move over here. Okay. And so I'm gonna say 4, sorry, I'm gonna say 3x minus 4y minus 12 equal to 0. Can I do that? Okay. So let's clean things up a little bit. Okay. Now, let's say I want this to be my passer and my fail. Okay, again, it's a little bit of mix, but not so much. Okay. Right. So, who is this guy? Somebody's over here, right? It's a passer. What is his XY combination? Is it bigger than 0 or equal to 0? Or less than 0? There's only 3 options. It's what? It's what? Okay, let's say this is 4. It's 12, right? But it's over here, so maybe 4. 12 minus 16 is negative, right? So this is all less than 0. So this is greater than 0. Okay. Okay. Okay, let me switch the problem around. Let's make this positive side. Let's make it negative side. What kind of function will give positive to this and negative to that? I want a function that say, I'm sorry, can I go back to x1, x2? Yeah, okay. Y equal 1 if, okay, was it 3 or 4? 3x, right? 3x1 minus 4x2 is what? Greater than 0. That's good. Right? 0 otherwise. Can I do that? So basically, I want a step function that looks kind of like this. Can you visualize that? Yeah. Think in another dimension. This is x1, x2, and this is y. So I want this to go up to be like a step function. So anything to the left here steps to 1. This thing goes below. Can you imagine that? Okay. It's gonna look like this. Can you see that? Yeah. Guys, who hasn't seen this? Because if you can't go on if you can't see this. You can see this, right? It's a step function. So I can't say partition function. The way I define partition function is to give you 2 values. If you're over here, I give you a 1. If you're over there, I give you a 0. That's it. That's how I do my partition function. Okay? Simple as that. Now, this partition function is only a function of certain quantity called 3x1 minus 4x2 minus 12, right? So this is some kind of quantity that you want to deal with. Okay? Okay. So hold that thought. Hold that thought. Hold that thought. I'm gonna clear. Let's call another function kokai, function of kokai. Right? I want this function to be 1 over here and 0 over here. Right? So that kokai is definitely exactly what we did, right? 3x1 minus 4x2 minus 12. Right? If it's greater than that, it's greater than 0, I give a 1. So basically, I want to draw that function. So one way that you can think of in terms of matrix multiplication is you have this 1x2, and you have 3, and minus 4, right? And then you say, is it greater than, equal, or less than 12? Yeah, see that? That's my question. That's my question. Except, yes, gives me a 1. No, gives me a 0. Okay? No, gives me a 0. So that's that. Now, how can I create this function? How can I create this function? Okay, let me try something. Okay, hold that thought. You know what an exponential function look like? Right? That's 1, right? So this is y is equal to e to the kokai, right? What's e to the minus kokai? Okay. What's 1 plus e to the minus kokai? Okay. Now pay attention. What's 1 over 1 plus e to the minus ก็ไป What's over here? 1/2, right? What's over here? What's 1 minus this thing? Go all the way to 1, right? Okay. We have something that looks like this. Asymptotically, it's like that, right? So this is like going down to 0. So you still have 1 left, right? So 1 over this is 1. So you have something that's over here, and you end up somewhere close to 1. What about over here? It goes to infinity, right? Where does it go to? 0. So this thing would look like this. Okay. Now, let's play with a little something. Let's say I want to plot okay, 1 divided by 1 plus e exponential, right, to the minus a. Okay. A from minus 10 to 10. See that? See that? So over here can be my distance. What if instead of doing this, I make this distance instead of a, I say a equal to, in our example, something like what? What was it? 3 and minus 4, right? Dot x1, x2, something like that. Okay, let's say we did that. Okay. And then minus 12. This is how I would do it. So I define the distance from this line as that, and I just do this. Now let's see if I can do this instead. So okay, so I don't have a here anymore. I have this, right? So I have x1, and then I have x2. Let's make it minus 2 and 2. Because see? This is the line that you get, right? So where are my passing students? Over here. Where are my, right? Oh, yes. Okay, go ahead. Okay, so you can see that this is what I mean by a partition, right? Right? Now, okay, the critical point is this. The critical point is I have to turn if that, this is an English language thing, right? If that, if that, if this, then that, if this, that, into a mathematical function. Is it perfect? Well, depends on what you mean. It's not perfect because it's not that sharp of an edge. Right? Okay? Because different, very courteously, I want you to be nice to them when they come back and explain what I just told you. Okay? It's not perfect because it's not a sharp edge. Having said that, remember I told you that there are some imperfection in my partition. Let's say, sorry, we do it again. The view is us, right? So the certainty is not the perfect. So if instead of saying 1 perfectly sure you pass, 0 perfectly sure you fail, this thing you will get a value of like 1 pass. Pretty sure you will pass, but give a little bit of uncertainty. So this function is actually perfect for our purpose. Right? Okay, let me repeat for you guys again. This function is a mathematical way of translating if there. If over here, get 1. If over here, get 0. But this function is not perfectly sharp, right? There's some movement. It's not perfect because over here, the guy along this line doesn't get a 1, doesn't get a 1, 9. Over here, the guy doesn't get a 0, doesn't get a 1, 2. But that's exactly what I want. Because these are the guys who I want to market. Right? The guys over there definitely pass. The guys over there definitely fail. The guys over here to the left, sometimes pass, sometimes fail. Maybe even 50-50. Right? So this is why this function is actually perfect for our purpose. So that is what the situation we want captured. Now, just as general regression is so ubiquitous, mathematicians calculate the perfect beta and beta. Same here. This is called logistic regression. The reason it's called logistic regression is because this function, remember I told you, 1 divided by 1 minus exponential a from say minus 10. Oops, sorry. 1 e to the minus a. 1 plus. Okay? If I didn't want to type this, I can do this. Logistic sigmoid A. Get exact same line. Okay? Because this function is called logistic sigmoid. Okay? Forget the word logistic, focus on the word sigmoid. What does that remind you of? Signaling. It's signaling that this is a 1. Right? It's the problem with signaling. I signal that you're over here, you should get a 1. Here you also get a 0. That's why the word is signal. So, but because that function, there are other forms of sigmoid, but this particular form of sigmoid is called logistic function. The other one is, I'll show you. This is also a sigmoid, except it uses from -1 to +1. So sometimes people prefer this. Okay? But anyway, they kind of equivalent. In fact, you can just sort of like squish this one together. So because the function that they use, okay, it performs a sigmoid, but it's logistic function. Okay. When you do something like here, that's why it's called logistic regression. Go home and Google logistic regression. Just as linear regression is ubiquitous, so is logistic regression. Ubiquitous. I would safely say that 10 years ago, every single bank in Thailand and the most of the world uses logistic regression to tell whether or not you are going to get involved. Okay? When you apply for credit, when you apply for loan, let's say 10 years ago, just 10 years ago, virtually 90% of the world's banks, all the world's banks, okay, would take your data, how much money you make, or your saving, or your education versus your variable, your years of experience working, so that is a kind of numerical variable, put in 30% of you into this logistic regression. And if the answer comes up to 1, you are likely to default. I'm not going to give you any money. Okay? So logistic regression covers 9% of credit risk modeling in 20 years. 20 years ago. Okay? That's that. Yeah, so it's up there. You don't have to learn your story. Yeah? Not quite. Not quite. I'm going to tell you something that you can go home and tell your parents. You guys know what a neuron is? Yeah, let's Google a little bit. That's what a neuron looks like. I'm going to use this one. I like this one. Yeah, this one is fine. So that's from Wikipedia. Can you see that? There, that's a nice picture. Okay. You have like 100 billion of these. Okay, roughly the same number of stars in our local galaxy. Not quite sure. Maybe I'm different by some order. This is your neuron. Okay, you have billions or hundreds of billions. I'm not quite sure which. Okay, each cell. This is a cell. Looks like this. It has a lot of roots, and it has a long output. Okay? Long output. Now this thing with all this is connected to other neurons and out here as well. Okay, but let's say that you take input from many neurons, but you only send to one neuron. Okay, right away, this reminds you of something. I'm taking input from a lot of guys, 10 of them, and I'm giving output to one guy, one of them. What's the linear regression problem? It's also taking x1 to xn, output to y, right? It's 1. Okay? So we start to get the imagination forward. Okay? I have a function that takes x1, 2, 3, 4, 5 up to xn, gives you a y. A neuron takes an input from another neuron, neuron 1, neuron 2, neuron 3, neuron 3, 4, neuron n. And then I send my output to another neuron. My output is called y. Okay? And depending on the connection strength, you see this has neurochemical in there. It has chemical in there. So the conductance is different. In other words, once you get the input, the neuron works by fire. So if a neuron that's connected to this guy fires, it gets multiplied by whatever is the conductivity here. So let's say it has high conductivity. Okay, so if this thing fires, it reaches here. But this one has low conductivity. So even though you get a firing signal, you get low signal. You can actually have the opposite, like a negative. Imagine, okay? In biology, maybe not. So what you do is you take signal multiplied by the coefficient, plus signal multiplied by a coefficient, plus signal multiplied by coefficient. Do this in n time. And then you have some kind of threshold signal strength test over here. The signal has to be greater than a certain number. In our previous example, what was that number? It was 12. So imagine that you have a neuron that only has 2 incoming neurons. Only 2 incoming, okay? By the way, the incoming leg is called dendrite and outgoing is called axon. So you have 2 dendrites. One dendrite is X1, is attached to X1. The other dendrite is attached to X2. And whatever signal I get, which is 1 or 0, I multiply by 3 and minus 4. Add them up. And I check whether or not it's greater than 12. If it's greater than 12, I fire. Signal is 1. If it's less than 12, I don't fire. If it's exactly at 12, I sort of like give it half a signal. Okay, in biology. So you can imagine that a single neuron, and this is the most important one, a single human neuron implements a complete logistic regression. So when I went to a lab, one of the first thing I said was, if you're still using logistic regression, you are a 1 neuron bank. Your entire credit rating department is as good as 1 neuron. That's it. That's what I would say. Yeah. Some people like that comment. Some people were threatened by it. But anyway, that's the real thing. 10 years ago, virtually 90% of the banks, all banks, United States, everywhere, were using 1 neuron to evaluate your credit risk. Because they only had 1 credit person. It is something more sophisticated that basically comes down. Okay? Everybody was a 1 neuron bank. Oops, I can't stop. Hey, it says my camera stopped. Right. So that's that. So, if you imagine that this is what 1 neuron can do, okay? Let's imagine a little bit further. Let's go to what you can do with just 2 neurons. This one is the same thing as what we saw before, right? Except I make 2 plots. One is 3D, one's contour plot. You can see in Mathematica, it's called contour plot. The other one is plot 3D, right? Now let's make them 2 neurons. So now I've got 2 neurons. What do you think happened when I add them together? Just add them. I get this. So already I get very complicated function just from 2 neurons. And depending on how I align my coefficient, right? Let's play around a little bit. Right. You have this, by the way, right? I can do that. Maybe not. Right? So you can see that the shape is very different. Even though you start, so imagine this is 2 neurons. Yeah? You have 2 neurons. Okay, let's stop that. Okay. So let's go back to our picture. this would be like one neuron. If I have another neuron that goes to map onto this one, that would be the sum in neuron, right? Now, in neural network, instead of having 2, why not have 10? Right? And if there's some over here, they are still neurons. They can keep going. That's what modern neural network look like. So here is where X1 and X2 and X3, X4, X5 comes in, right? And this is the dendrite. This is the neuron. The weight is over here. X1, W1, X2, W2, X3, W3. Add them all up. Check the threshold. Normally threshold is called theta. Okay? Subtract that and then pass it through this and then fire. And the output of one neuron is this. If you have 2 neurons, you do this. If you take the 2 neurons and you compound it, right? It becomes a neuron on top of a neuron. Then you have this. So this is called multi-layer perceptron, right? And then the output. Now, the output here, by the way, can be 2 things. If this one is also a neuron, you can use this for classification. If this one is just a summation, you can use it for regression. Simple as that, right? Because you can have, you know, coefficient, positive, negative, whatever. So right there, you learn what was basically state of the art. Yeah, and became a state of the art banking only maybe 5-10 years ago. So banking is kind of now, if you have this, first of all, how does it work? Again, this is just a neural network, just a template. Think of it as a template. It's a blank template. I say I have X1, 2, 3, 4, 5, 6, 7. I have 4 neurons over here, 3 neurons over here, and this one is a neuron. I just leave it like that. That's like my beta 0 and beta 1 being starting from 0. Yeah, it doesn't do anything. So it has to do 2 things, right? It has to do 1, the learning task. 2, it has to do something useful. So the learning task here is now instead of having just a line that says where you are on the coordinate of this group, I can take something like your grade from homework, your grade from high school, or your whatever, I don't care. Attention span, I don't care. Whatever variable makes sense. Let's say I have 7 variables for all of you. Right? Now imagine that we can visualize 7 dimensions as if it were 2. It's still a separation problem. But now I don't have just a straight line anymore. I can do curvy lines. I can do really twisted lines. So what's the problem with neural network? Get too greedy. It's not going to learn. It's going to memorize. Right? Remember that? I want every children to learn from examples. The examples aren't perfect, but noise in it. So I want the children to learn the essential functions from X to Y, but allow for some noisiness in the input. Right? So it's a generalize. Right? But if the child wants to be so smart, please a parent, remember everything they think about an apple, everything they think about an orange, they overlearn. In other words, it's learning all the zigzags. That's called overthinking. Right? Overthinking. That's no good. For example, I give you a whole bunch of apples and orange. Maybe one apple has a weight that's smaller than 50. And it's still an apple, right? The child remembers it. So later when you see an apple that's upper weight, upper size, doesn't know, doesn't mean it's an apple. Because for some reason, from that sample, there's an orange that's exactly like this. So you memorize, you internalize, but you don't generalize. It's not learning, it's overfitting. Right? You learn too much. You learn too much. Okay? You learn the individual cases. You don't learn the general concept. Okay? You don't learn the general essence. You overlearn. That's what it comes down to. Now, if I can do this with 2 neurons, I think I made another example with 3 neurons. That's even, basically just add them all up. You can do all kind of stuff. Now, the function can be different as well, not just logistic function. This one is called a ReLU function. It's more popular nowadays. When I was doing neural network research, we were always using this. The reason we were always using this is because it was modeled after human neurons. Deep learning uses this. The reason they use this is because once you get to the deep architecture, that's that part becomes the problem. In other words, it doesn't know what to do, so they prefer the speed. Let's ask the opposite question. With linear regression, you can learn linear. You don't learn anymore. With neural network, if you have enough neurons, you can learn individual data points. You can memorize. Okay? Let's put aside the question of overlearning. Let's ask the question: what if it's not noise? What if it's just the problem is so complex? Right? You want to learn it. It's so complex. It's not noise. It's not noise. You want to learn it. How complex can a neural network learn? Question was, if you have arbitrarily complex functions, very simple functions, can the neural network learn that? The answer was yes. And it takes a lot of mathematics to prove. But in saying that, you don't even need many static neural networks. You have one layer of neural network. Have enough of them, you can synthesize any complicated thing. Let me say that again. What you saw with this one, it's just this, right? In one dimension, it just looks like that, right? And if you have another one that's in another dimension, so it kind of looks like some kind of cut. The question is, can it do something more complicated than this? The point is, yes, not with just 2, but with 10, 20, 30. And to prove that mathematically, yes, you can fit any function whatsoever by enough neurons. If you have enough neurons. Now, theoretically, enough means infinite. If you have infinite number of neurons, you can approximate any function. It's called universal approximation theorem. And even though when I was a master's student, just going through this one theorem takes the entire class. So it's a little bit of math. But I can give you the intuition. Many of you came from high school. Well, not many of you. All of you came from high school. You remember a trigonometric function, sine and cosine? You remember that sine and cosine can add and subtract from one another? Every time you add more, you get funnier looking wave. In fact, FM synthesis, our computer makes artificial sound with the 80s, retro of something. All it does is a whole bunch of sine waves add together. And the sound of a trumpet, as opposed to the sound of a horn or sound of a violin, is that complexity. It has the basic same complexity, same frequency for note C. So it plays the same note, has the same basic frequency. But whereas one note would look like this, okay? Whereas one of them looks like this. This is simple. This is simple sine wave. It's a sound of something like that, right? A piano might look something like. A violin might look like. I don't know. Okay. The point is, even though you have the same periodicity to make the tone C, that complexity that gives you the timbre of the sound. Now, even if there's a Fourier theorem in mathematics, say, even if you don't want that, you just want to draw a mountain. Let's say you went to okay? Let's say you're a mathematician. You went on a trip and you saw this beautiful picture and you want to send it to your girlfriend. You don't have a camera. Okay? But you have Mathematica notebook. Okay? In theory, you can send her sum of AI sine of BI theta I going to, let's say, 500. And she can draw that picture. In theory. It's a composition of sine waves. Well, universal approximation is like composition of sigma. You can also do this. In fact, if you didn't come from a Fourier, you can also send your picture, this picture to your girlfriend, okay, and then have a whole bunch of coefficients. If you send this, she can plot this out in Mathematica and get just this beautiful picture. Yeah. Now, in fact, I should send you this. Let's go to, I think, YouTube. Drawing. Drawing the Beethoven with Fourier. Here. It's the same thing. I can literally draw a picture. Well, the tree will be one-dimensional. If I have two-dimensional, I can literally draw a picture of, let's see, where's the picture? Yeah, see? Now, a sine wave is a one-dimensional thing. A circle is a two-dimensional sine wave, right? The circle. You want to add the sine wave together. In this case, you add circles together. So that's what this does. I just add a whole bunch of circles together, right? And then draw a line. See? So this is one circle. This is another circle. I add a whole bunch of circles together and I can make this line. Anyway, it's the same thing. It's the same thing. You need that neural network and learn any complex function. Okay? And learn any complex function. Okay, there's nothing here. So that's basically what have we done here? I've introduced the most fundamental concept of machine learning, yeah, which is a neuron net, yeah, a neuronal. Yeah. We'll, in terms of technique, we learn other things. We learn other things, more simplistic. Yeah. But this one is actually simple to explain. The reason I chose this, by the way, you know why I chose to explain neural network first? Because my assumption was you understand linear regression. Okay? I would have done the other way around. I would have maybe, really good to have, like, you know, to have knowledge about linear regression. But it's not so bad. It's not so bad. It's a bit tough. But if you had last year linear regression, or even in high school, they teach linear regression in high school now, by the way. Okay? We have linear regression, we have logistic regression. You know that they do the problem we want to do, which is regression and application. So logistic regression, application. Okay, so, okay, remember that? Logistic regression is a classification tool, but it's done with you want something more complicated, you have to create this platform, this template for the machine to learn from example. It's the same thing that the biology gives you trillions of neurons, right? So biology didn't evolve you to have one neuron. It evolved you to have billions of neurons. But when you were born, all these neurons were random. It's like random coefficient. Think of it that way. And because your brain is so complex, if I gave you 3 years to grow up and become a functioning adult like chimpanzee, basically you don't have enough time to learn all the right coefficients in your brain. So it's like your brain in the 20 years of your life is all about tuning the conductivity of the dendrites of all the billions of okay. Okay? That's what it means. And when I said, in the beginning, you were a child who learned this behavior, that's also a neural function. It's saying that this is a contract. Basically, to be an animal, this is what you have to do first. I'm looking at this. This is a flat field, right? It's a flat field. It's like a picture, right? First, I don't know anything. It's a picture. But I do know this. When I move my head, this entity goes to the left, but the background doesn't. The far background doesn't. So there is an edge there. That's how I recognize. So before a child recognizes the father or mother for who he is, has to recognize there's an object. In fact, that's what a camera does. The first facial recognition in camera is not a facial recognition at all. It doesn't recognize the face. It identifies that over here there is a face. Okay? First generation of digital camera, later generation of it just detects the face. It's called facial detection. It detects the face. Now, as they become more sophisticated, maybe you can take pictures of the children more, right? And that newborn gets very excited about the child or nobody else. Then maybe there's a feature, say, focus on my child. Okay? And if I take a lot of pictures of my children, it's going to recognize that face. And so I go to a kindergarten, say, hundreds of children all over the place. Maybe it's not going to just detect 100 faces. It's going to say, where's the child? And focus on that. Never mind that face on the other. It can be done, that can be done. I don't know if that feature is available yet. But certainly it's very easy. I think iPhone is able. Okay. Well, maybe iPhone 15 or something. But it's a very simple technology, by the way. It's doable, really doable. Maybe it's not yet, they haven't got the bug worked out, but that's a problem. Okay. So this is how, so you should at least have something. First of all, as a bonus, you learn linear regression today, 2 minutes, 10 minutes, whatever. Okay. Second of all, I keep reminding you of the fact that you have to go back to the basic example. Ordinal, ordinal, right? Ordinal, interval ratio. Those things you can't forget. Now, if you come to problems and you want to do binary classification, what to do is the neural network, then you know that the last node will also be a neuron because that has to end up with a 1 or 0, right? But if you're doing some kind of regression, like estimating the height from estimating your height from your parents' height, maybe actually estimate your height from the measurement of your hand, your feet, something like that, then the output is going to be a real number, continuous number, not 1 0. So the last node will be the summation node. Details will be more forthcoming. Don't have to worry about the technique because you don't know that yet. But I have given you, let's say this is the universe of your problem. And this is my bet. Yeah? My bet is if you go through any kind of analytical problem that requires 95% of the time, it would be either supervised learning or unsupervised learning. Maybe you can split that 60-40, I don't know, 60-40 or 50-50 or 70-30, more supervised learning and a little bit less unsupervised. Today, I have given you the basics of supervised learning, citing the example of neural network. Okay? It's a network of neurons. Each neuron is similar to what I covered earlier. So think of that. Now, next class, it's important that I cover the elements to the unsupervised. Now, we have fairly decent amount of time to cover. So next week, the plan goes something like, next week, I will go to unsupervised learning. The week after, I'll come back to supervised learning again, except I will pick up the other technique, like decision tree, like forest, all kinds of stuff. These are very useful. In fact, I can tell you right now in my consultancy work, I actually use that. In actual instant, in terms of counting the number of projects, I've used it more than neural network. Ultimate outcome. Final outcome. I've ended up more just because of the problem. Okay, not because if you're gonna do facial recognition, you're gonna do neural network. It's the way around. But if you're gonna do something like credit risk modeling, well, you wouldn't do linear logistic regression. That's too simple. But you might not go to neural network. You go something else, like decision tree or maybe. So that in my memory, just because I have been dealing with relatively simple problems. Okay. The neural computation model hasn't become a must in my area. Okay. But as I hope get more then neural network is going to be basically okay. So then the timing goes basic supervised learning, unsupervised learning, non-neural supervised learning, and then maybe afterwards neural learning, but very deep. Then you have all the tools, basically. But I would probably try to stay out of it. I want to do it as much as I can. I'm still having second thought, by the way, about having this project phase because you guys are. Right. I mean, I really was. Funny enough, I'm teaching MBA, and I thought their class would be this like lecture how to. It turns out they want to do a project, and so eventually Satsin bought Mathematica license for all. So all the students there are doing project with me. Yeah. So think about that. I haven't required Mathematica as a tool, but it's much easier. Next week, in fact, I would show all the programming basics at some point.